Cool. So we're now talk about chapter 25, which is more model. And in essence, most of this chapter was basically about how to apply the things that we've learned in the past couple of chapters into like real life problems where we might have our data in a data frame. How do we split it, apply models and evaluate the performance of these models? And again, it sort of uses this grouping package that was briefly looked at and lists columns in order to do that. So I'll go, I'll go briefly through the book and then the examples in the book. So basically, throughout this chapter, the first main focus is like how to create these list columns. And why sort of it's important and how like what problems it solves. The three or four main ways that we can create such columns, and how do we then, after creating and using them, simplify and get our data in a tidy format, basically. So we're using the same data set from the Gapminder package, just like we did before. And again, to start with, we're sort of plotting the overall life expectancy over time for each of the countries. And this is quite a busy plot, and it's not supposed to be an example of what we'd actually use in real life. But we see that overall, there's a general positive trend in most countries, but there are some countries where this trend clearly doesn't seem to apply. So basically, here's like how we would sort of look at a single country. And again, this is the method that we'd kind of used in our iteration chapter, where when we want to analyze like a set of data, let's say in this case, the relationship between these two variables for a number of countries, it makes sense to first figure out how you would do this in just one country, and then expand it to all of the countries using the iteration patterns that we learned. So if you look at just New Zealand in this data set, if we focus on just New Zealand, we can basically divide, we could divide the signal, which is like this full data, into a linear trend overall and the remaining pattern. So if you add this line and this line, you get this line. So linear trend, and here we see this double dip, which we can see here. So this basically, this residual plot over time tells us that initially our model was underpredicting the actual values by a small amount, and then overpredicting, therefore the residuals are negative for this dip here. But overall, we can see that when they're not huge in size. And if we then want to apply this kind of analysis to all of the other models, how would we go about that? And the suggestion in the book is that we would nest our data frame. So the idea with nested data frame is kind of similar to grouping, but it's not exactly the same. So whereas with grouping data, basically, it's kind of like we group our data according to the variables that we want, and then we nest. And what happens when we nest is that we basically take all of the data where country, let's say in this case, is equal to Afghanistan and continent is Asia, just like we do with group by, and then we now have all of that data as the value of this cell. So we can link, we in essence like chop up our data frame into different pieces and then nest it into this big data frame where we can basically relate data to the continent and the country it refers to. And why is this useful? Why not just do group by and apply things? Because this way we can basically have, you can kind of think about this as like almost like a catalog, or at least I think it makes sense to me to think of it like that. So for each country and continent, we now have this catalog, this big data frame where we have one column which contains data, and later on we'll have other columns which again contain, for example, the model statistics, and much more information. In this way, it's a lot easier to find, to basically link this data frame of data to the next data frame of, let's say, model metrics. So yeah, so with this nesting, we basically create a data frame where for each row, we have this data column, which itself contains data frames. Is everyone kind of, is that clear, or do we need to like go into more detail?
Yeah, that's good with me.
Yeah, I like the catalog idea. That's
Yeah.
really helpful.
Cool. Yeah, so, and just like we did before, and like fitting models, for example, for New Zealand, in essence, that's what we've done here. So to get the New Zealand data, we filtered our data frame to have country called New Zealand. Now, this NZ data frame is in a cell like this, where it says New Zealand here. So that means that we can apply whatever we applied here in order to basically add predictions or fit a model and residuals, etc., to all of the countries, which is the idea with our sort of iteration chapter. So one of the, sorry, let me just, there was another example shown in the book of creating nested data frames, but I guess we'll talk about that, yeah, a little bit later. Yeah. So yeah, so here basically they're defining a function which is literally just like this linear model, and we could apply it to our countries in the data column here, this column. But there's an even better way. So if we did that, as we know, map gives out a list as its output, which is great, but we basically, it would sort of defeat this idea of a catalog, right? Like we've gone from a data structure, if you just focus on this bit here, we've gone from a data structure where we can easily relate data to, in this case, country and continent, into having that sort of organized data structure and the list that we derive from this. It will be much better if we could continue expanding this catalog of data, model, and everything else. So, and the way we generally do that is using mutate in data frames. So we could do exactly that and basically create a new column where we basically map like the linear model function onto the data column. And now we basically have a linear model, basically a list of linear models that forms our model column. So now we can basically keep everything organized. And again, if we wanted to filter to find, let's say, all of the countries and data and models that start with an A, we can easily do that. And we don't have to worry about sorting our model list, which would otherwise be separate from this data frame. Or similarly here, they're looking at, let's say, Europe. So this is the advantage of using nested data frames and using these list columns in data frames. Like the plotting we did earlier and any other analysis might require the full data rather than this nesting. So in order to go into a more tidy data structure, we can unnest by using the unnest function. And we need to say which column we want to unnest. And when we do that, we basically go into, we keep everything else the same for each row of this. So basically this residuals table is 12 by 5. So we basically expanded 12 times while keeping everything else the same. So we said, in essence, we expand the whole data frame so that now these residuals are like have one row in each actual row rather than being in a table like this, like so. And the other columns are just repeated, as we can see here. Here. and this year life expectancy, population, GDP, and residual. These were the components in our residuals table that we got from add residuals, I think. And obviously, once we have that, we can plot it in all the shapes and forms that we love to plot things, and see how well our model is performing overall, and if there are differences in the performance of the model, let's say by continent or any other way we want to facet things. So we still, like, this is a good way of keeping the data organized and minimizing random errors that would essentially be invisible unless, you know, they looked odd and you managed to figure out what was actually going on. Any questions?
No?
No, thank you.
So basically, by looking at this, we can see that just like before, just like we've noticed before, our model is performing much worse for the life expectancy versus time in countries in the continent of Africa compared to other countries, and also for a few countries in Asia as well. It's not doing really well. And now we can also see that the trends is also, like this overall trend in blue, is also slightly different between continents and in the residuals. So we can investigate further the quality of the metrics. And the package we use for that is this Broom package, and especially we're looking at the glance function, which basically gives overall model quality metrics for whichever model we provide to it. And again, just like we did before, we can use mutate so that we keep the data all in one place. So we say whichever column name we want to use, and we apply the glance function to each of the models that we had in our model column. And we can unnest it so that we can plot and see what's happening. So there was, I didn't manage to see any difference with dot drop equals true. And I also get this warning that it's deprecated. I don't know if either of you has managed to use it. I've still, went through the whole chapter just fine without this, but I couldn't really replicate any of the differences that they're talking about. Did anyone else actually see any difference when they use drop equals true?
No, I think it was the same for me. Said it was deprecated, and I didn't really take it any further.
Yeah. But yeah, everything else still worked. So my understanding based on the commentary is that this would drop everything other than the glance column that's nested. So in our case, the data, model, residuals, etc. But it no longer does. We don't have to worry about that. And yeah, so and we can plot it to see the models that were fitted. And here, each dot corresponds to a country, the data of which we fit this linear model. And closer we are to 1, the better the model fits to the data. So this is one way, well, another way basically of seeing how well our model fits the data. And again, we can see unsurprisingly that the worst models are for countries in Africa. And in one of the exercises, they basically asked what's a better way of showing this, and I thought a violin plot, and this swarm package that they recommended was a good combination to see the distribution of this data in a more clear way. And then we're basically plotting the raw data that went into the models, where the models performed really badly. And yes, the data is indeed not very linear, therefore a linear model fit on this data it's not surprising that a linear model doesn't perform really well. And there's some explanation as to why this trend exists for the time period. So in the first exercise, basically the idea was like, can we fit, if we fit a quadratic model, would it perform better? In a way, it's a similar, more closer shape to what the data looks like. So how would we fit that? And how do we interpret the coefficients of the quadratic? And there's also a suggestion to transform the year. So here's, so basically, the linear model is in essence, y is mx plus c, or like whatever, theta 1 plus theta 0, etc. A quadratic model takes the form a times x squared plus bx plus c. So in our case, our x is the year and the y is the life expectancy. So we're in essence, we're saying life expectancy is explained by year squared and year. And obviously the c is also the coefficient that we'll get from our model. So I've basically put together the example we had for linear and slightly changed it to fit the quadratic model here. I added the x squared term. And also based on their recommendation, I've also created this like centered year variable where I remove the mean, therefore having the mean equal 0 from each value. And again, just like we did before, I calculated the residuals, and also the model metrics using and unnested the glance in a variable called model glance, and unnested the residuals into residuals. Underscore q for this is what they look like. So compared to before, the residuals are smaller in all countries, but we can still see the performance isn't hugely, is still not very good in some African countries and some of the Asian countries. So we've not removed all of the problems. And if we look at the R squared improved, we basically have only one value less than 0.25, whereas before we had many more. If I scroll up, this is what we're comparing again. So we had like a bunch of values between 0.5 and 0.25, and these were what were called bad fit here, less than 0.25, about six models. So this applying a quadratic model has definitely improved the R squared metric in other countries as well. And if we look at the same data that we saw before, so the countries where our initial linear model performed badly, and we look at the performance of the quadratic model, this is it. And I've included like the old R squared and the new R squared for each of these countries. So we can see there's significant improvement in all of them. But it's like, I think this doesn't necessarily mean that this is a better model, because in essence, what this model is saying, wherever the peak is the highest life expectancy. And then for every year after that peak, we expect life expectancy to drop, especially if the coefficient of the x squared term is negative. And I think this one's the only one that seems to have a positive coefficient. And I think we wouldn't necessarily want to use this to extrapolate, because clearly most of these are showing a positive trend, whereas our model is kind of focused on this shape a little bit too much. As I said, yeah, for every year from where the stationary point of this quadratic is, basically. Life expectancy is expected to decrease if the coefficient of the x squared term is negative, or increase if it's positive, which is only one case here. But again, here we can see this model is doing a terrible job of actually predicting, and it's not doing, in terms of r squared, isn't doing better than our linear model. And yeah, the rate of change, because it's x squared is kind of 2x, and the coefficient of the x term, so like the centered year term, can move the peak left to right, and the constant moves it up and down. I think this is a lot harder to interpret. The linear model is a little bit more intuitive, but yeah, as I mentioned, I think the main reason why I wouldn't say this is a better model is because of problems with extrapolation. And I think, yeah, it basically picks up on a transient signal as if it's the main feature of the data. And that, yeah, we could have a better way of modeling this transient. In essence, like this was, increasing and something happened, but it's going to increase again. And we see Zambia, the same thing. So it will probably be, there are better ways of modeling this transient. Yeah, it's the shape of the data.
Yeah, I mean, I would agree. So the modeling you've done definitely is perfect, but when you come to the interpretation, then it becomes a little bit hard to do because of the y. I mean, we're having the model quadratic in terms of the y, which is the year. But however, the best thing that you did here, which was also good, was the standardization or whatever, the normalization of the year to a specific reference, because that helps you actually interpret it better or even easier.
Yeah, I actually haven't tried without it because, when they give a hint, I take that as you'll struggle if you don't do this.
yeah. And I'm saying this because like I was doing some demand model for air traffic. And basically, I needed to show that the demand changes quadratically. So at a certain distance, for example, about 500 kilometers, then the demand trend is reversed. But you cannot identify this 500 meters or 500 kilometers if you don't really do something like this. You need to try to get the reference point, then it becomes way easier for you to write that out rather than drawing everything. Nice graph.
Next question. Oh, sorry, were you saying something, Ruth?
No.
Okay. The next question was, other methods of visualizing the r squared per continent. I found the B-Swarm package quite good actually. They have two functions for plotting, which we can play with here. Okay, now I need to run the whole thing. Yeah, so this quasi-random keeps the data a little bit like closer to where it needs to be, whereas the bee swarm kind of sticks it all together. But then you can see the distribution a lot better, kind of, yeah, a bit like a variant plot. Yeah. And the third question was to create the last plot here. We needed 2 steps. We created a data frame with 1 row per country and then semi-joined it to the original data set. Is it possible to avoid this join if we use unnest instead of this? Yes, we just need to basically, so bad fit, as a reminder, was the models where the r² is less than a quarter. And if we look at this data, we basically have our data still here. This is the original data that we fit the model on. So all we need to do is basically unnest the data as well and plot it. So instead of doing the semi-join, let me hide that. We just take bad fit, unnest the data and plot. We get the same plot. Cool.
Yeah, pretty cool.
So the next section talks about how we create list columns. So far, we've basically done, we grouped by the variables that we wanted to keep and then nested. And this is the first option. We can also create list columns from using other list columns, which again is what we've done in our data set. And we can, yeah, unnest them. So for nesting, what we've done in the example was group by the things that we want to keep and then nest. The alternative is basically to, without the group by, is to explicitly say which columns you want to nest. So in our case, the gapminder data set has country, continent, year, population, GDP per capita. When we grouped by the first 2 and nested, we ended up nesting the other 4. Another way of doing that without the group is these 2 are equivalent. Next way is using mutate. So if we use mutate and a function that returns a list, that will generate a list column. So the example that was given in the book was basically some character data separated by a comma. And if we use the string split function for each one of them, we'll get a list. And inside a mutate, this is how we could get a list column. So this is what we start with. And yeah, once we sort of, this is sort of after we unnested. So I guess I could just run this bit to show. So here we basically get from A, B, C, we get a character vector of length 3, which is A, B, C. And when we unnest that, we get from A, B, C, we get A, B, C separated, and the same here. Or the other alternative was from our iteration chapter, where we simulated some data using a number of different distributions. When we use this just invoke map, if we put that inside a mutate, then we can create basically a list column. So we have the name of the function, the parameters used, and then the random sample for each one of them, because we basically have a set number of, we've set the sample size to 10. So that's another way of creating list columns, which is basically using a vectorized function that returns a list inside our mutate. The third way is quite similar, but instead of mutate, if we use summarize with a function that returns multiple results. And the example given in the book was the quantile function. And if we just look at what this gives on just some data, the quantiles of the sample. And here in this case, we can group by one of the variables and then look at the quantiles of that range, where we get a list, and this contains sort of the same data that we were seeing, but for each of the 3 different values of cylinder. What this is missing, if we actually unnested, is the positions of these quantiles, and we would know if we'd sort of sorted them, we'd know that Q1 comes before Q3. But one way we can add them in is by explicitly stating the probabilities. So would sort of add the probabilities as a list and the quantiles as well for each of the different values. And here it's a lot easier to see that this is the Q1, Q2, etc., and this is the minimum for this value.
Mm.
Any questions? Cool. And the fourth and final way is if we use this end frame function on a named list. So here X is a list, is a named list. Each of values have a different length. And if we use end frame, we basically get the name, well, that element as a list as well. So this was very interesting because we saw something similar to this in previous chapters in Tibble, where we can turn another way we can turn a name list into a data frame or a Tibble is if we use as Tibble, but this this basically makes these column names and the lengths need to be the same. So if I do that, this is like the sort of transposition table as as like another column of the data, like for example with like the catalog idea when we use end frame.
Mm.
And we can basically create like, this was just something, for example, like a summary of the values using the map. And generally it's recommended when you're creating list columns to make sure that they're of the same type. Just to make like all the other operations more consistent. Any questions?
No.
No.
So the next exercises, well, there was a lot of brainstorming. So question 1 is list all the functions you can think of that take an atomic vector and return a list. I thought of a couple of string R functions like split and extract all, and all of the map functions. Any others from either of you?
No, from me. Well, I'm yet to understand the split, the string function, but at least the map, the power functions, I know about those ones.
Yeah, I didn't get any others.
Do you want to like?
Yeah, I would want to try out the string functions because actually every time I'm trying them out, like in a data frame, you know, when I want to apply it to a specific cell, I kind of like use debugging to know what I want to put out. So it'll be nice to see.
Cool. Let's try one. So in essence, we're basically, if we had our data, was it we're using the list? No, atomic vector. So our strings are, let's say, and select all strings. Say we want to select all the vowels. I don't know. So we do. Is there a shorthand for vowels? Probably not.
No, yeah.
Do that. So for the first one from hello, we got E and O. And the second one, OOE. So we gave it an atomic vector of basically a character vector, and we got a string. We got a list back where the first element are the matches, matches of this regular expression from the first value, and the second element for the second.
So just a rough something I also want to try out. So is it possible for you to make the strings as a named list, then use mframe to turn it into a data frame, and just extract the first vowel?
And then mframe. So instead of strings here, to do mframe.
Okay, yeah. Will it work? Oof.
Oh, our list.
Interesting.
How do the name list again? Does this have to be a string?
No. So I meant if you turn strings into a data frame, then you use mutate to create a new column where we put the first vowel. Okay, yeah. I think it still works on that.
I think it may not. Yeah, I'll make these strings. Although I'm not sure. Yeah.
Can you run it again?
Mm-hmm.
Oh, cool.
So yeah, we basically get a list as an output. And if this wasn't a data frame, so if we basically had like something like this, where we have table and we say x equals like if this was a column.
Mm-hmm.
And then I'll just quickly actually move this down. And then we did here y equals string extractable. run that, we should get the list column. So we get a list column where the first one is a character. It contains 2 characters, and the second one,
Yeah.
did like unnest here, would see the E O O O E. Does that make sense?
Yeah.
Y. So from hello we get EO, from goodbye OOE.
Okay. Yeah, I see. But also basically, if you want to, because it's gonna be a list anyway or a vector. So if you want to, we can actually just try to index the Y from the mutate.
Index the Y.
Yeah. So like at the end of string extract, you put like the block brackets. No, inside the mutate, inside the mutate.
Oh, yeah.
Yeah.
Then there won't be anything to unnest. So
Yeah. Yeah. Cool. Oh yeah. Okay. Now I know I'm not always running crazy.
Okay.
Nice. Thank you.
Cool. And for question 2, brainstorm useful summary functions that, like Quantile, return multiple values. The only other one I could sort of come up with was range, which basically returns the minimum and the maximum of like a set of numbers. Anything else from either of you?
No.
I think I just found some on the internet. 5num and boxplot.stats. I hadn't come across them.
Oh, they start geoms in ggplot basically.
Right.
And yeah, here they're asking what's missing in the following data frame. How does Quantile return that missing piece? Why isn't that helpful here? So if we just run this, this is the, we've sort of seen this code earlier. My ask video stopped responding. I don't know what to do here. Basically, the thing that's missing are like the positions of the quantiles, like we discussed earlier. And you can make the quantile function return this by saying names equals true, but it returns it as the names in the list rather than a separate column. And that's not very useful here because when we basically like unnest, we lose the names. So the way to solve that would be, just like we did before, to explicitly give the positions of like the probabilities and add that in as in our summarize, basically. That's what I mean. Yeah, so basically this is the output we get, but we don't know whether this refers to the minimum, Q1, Q2, Q3, or Q4, etc. So we could solve that by adding the probabilities explicitly. And for question 4, what does this code do? Why might it be useful? So this code, right, this is what they did. I thought it looked very funny. It basically, we group by cylinder and we summarize all other columns into a list. I don't know why this might be useful. I guess if you wanted to calculate any other like metrics, but you could just group by and calculate them anyway. So I couldn't really come up with any reason why this would be useful. I don't know if you have any thoughts.
Yeah, but I mean, so just imagine if you have the columns as years and you want to get like I don't know, you want to compute some summary statistics at once of course, then later on you need to do unnesting or something like that. Yeah, because like this is just horrible to work with.
Yeah.
Yeah, but I think for me, what I've used at one point was instead of using summarize all, I used, you just pick one summary statistic to do.
I suppose I've personally not used these like summarize all, or there are like variations, mutate at or if, and now I think you're supposed to use across for these, but I've not actually I'm not very familiar with them at this point.
Yeah, summarize all, not really.
Cool. Shall we move to the next section?
Yep.
So this section is about simplifying list columns. So once we've created our list column using one of the 4 methods that is mentioned and utilize them for, let's say, fitting a model or extracting residuals, etc., we'll eventually want to basically simplify them and turn them into like a tidy data format or like a regular data frame at some point. So here they're showing us a number of ways we can do this. So if we want a single value out of our list, then we can use mutate with a function that takes basically a vector or a list and returns a single value, such as like maps that we're familiar with. Or if we want many values, we can use unnest like we did before for our plotting of residuals and other metrics. And this will basically do the opposite of nesting. So some examples. We basically start with this data frame that contains first 5 letters, numbers, and a random sample of numbers. And here we're basically taking a list and calculating, basically performing an operation on it that returns a single value. So what's the type of this list? So the first one is character, the second one is integer, and the third one is double. And again, another example of something that takes in a list or a vector and returns a single value is the length. So how big is this vector? 5, 3, 5. So that's one way of simplifying them. And similarly, we can use map. Here we're using the map functions to get a certain named value. So in the case of X, we want the value with the name A. In the second one, we want B. And there's an argument in map family of functions called .null. And this is basically, if you can't find the value with the name B, use this instead, which is what we're getting. So these are two ways of basically 2 examples where we can go from a vector into a single value and therefore summarize our list column. The second one is the unnesting rows, which we're quite familiar with from our plotting before, but here's a simple example where we basically have 1 and 2 in our X and a list of 4 numbers and a single number. And when we unnest, we basically repeat this 1 4 times in order to, well, until we expand, basically until we unnest the Y column. You can also apparently simultaneously unnest lists if they are of the same length. I didn't know about this. This is quite useful. So here we basically have like A and B and 1 and 2 in this row and a single value here. And when we unnest both of them, instead of going, A, A, B, B, 1, 1, 2, 2, we in essence expand them simultaneously. This only works if they're of the same length. If they're not, then the previous repetition pattern is applied, which is here. So here we have a single value versus 2, or 2 values versus 1, and here it's repeated. So A is repeated twice to unnest the Z, and here 3 is repeated twice while we unnest the Y.
Mm-hmm.
So exercise 1, why might the length function be useful for creating atomic vector columns from list columns? It will be useful because it basically returns the length of each element in a list, regardless of the type. And I had a bit of fun here trying to see what we'd get. So I created a list with a tibble, with a column of a tibble, some ranges, some strings inside and outside of like vectors, just to see what would happen. And basically what you get is like for tibbles, you get the number of columns, which makes sense because in essence, data frames are lists and each element is a column, as we sort of covered before. If you just take a particular column, i.e. an atomic vector, then you get the number of elements in that vector. And again, similarly, with this range, we just get 2, which is as many, this is 1 and 2. With strings, you basically, this is treated as like a character vector of length 1. So these two things are, like the same thing. So we just get 1, which I thought was a little bit counterintuitive, but I guess this is why we have the str length function, I think, from string out to, if we want to count the number of characters in the string. And again, for the list, we get the number of elements. And this is like the example from before. I just wanted to see. So with nFrame, we basically would have 2 columns. The first column with the names and the second column with the values. Therefore, we get 2. Whereas if we did as tibble, the names would become the column names and the values would become the values. So if you want to see that, I could just run that section. So as tibble, this is what we get. Whereas if we do nFrame, this is what we get. Therefore, when I run this, basically this gives 2 because there are 2 columns, and this gives 4 because these would become the column names. So yeah, but long story short, length gives the length of each element in a list, and therefore it will be quite useful.
Havva. But so if, for example, if you take the length of hello,
yeah,
that should give us 5, right?
That's what I thought as well, but it doesn't, because I guess this is the character vector of length 1, which contains the word hello. Whereas if you'd need to do like str length, I think.
Yeah, because I'm thinking, do I have R? Okay, I'll try.
Yeah, but like I found this quite counterintuitive, because in Python, for example, if you do len, which is the Python equivalent of length of a string, you get the number of characters, but not in R.
Yeah, that's crazy.
Yeah.
All right. Yeah, so length works. Hold on a second. I need to come back here. Okay, so this is length, not length.
I think we have like n cars or something like that, where it's like, yeah, length of hello is 1.
Okay, interesting.
So number of characters.
Okay.
The second question is, list the most common types of vector found in a data frame. What makes lists different? The most common vectors found in data frames are, well, some of them are like characters, factors, numeric, logical, integers, etc. And lists are different because they don't have to contain all like the same data type, whereas atomic vectors like these do have to. Therefore, in a list, you could store any of these things all together, and that would be fine. Although, like, if you want to use them using like the methods we learned in the book, it's highly recommended that you keep them compatible, if not identical. So like integers with sort of numeric is fine, but you don't want to mix, I don't know, characters with integers, even though like there's nothing stopping you doing that from in a list. And in this final section, a little bit more information about using the Broom package. So you can use the glance function to get information basically for a model. So it returns a row per model and gives a model summary like we used before. So it gives us metrics like R², adjusted R², and many more metrics. We can also use the tidy function, which returns a row per coefficient of the model, and then it gives us information about each coefficient, whether it's like how variable it is or p-values, etc. And we can use augment, which returns a row for each row in the data. So we're going basically like more and more detailed, and it basically adds extra information for that data point. And that's it. That's it for this chapter.